Section 1. Time dilation and the relativity of aging. To understand the possibility of traveling through time, one must first step gently into the concept of time dilation. The idea that time does not tick uniformly for everyone, everywhere, but flows differently depending on speed and gravity. It is a concept that transforms time from a fixed river into a malleable, flowing current shaped by the universe itself. Einstein introduced this idea over a century ago in his theory of special relativity, which describes how time and space are intimately connected. According to the theory, as an object moves closer to the speed of light, the passage of time slows relative to those left behind. In other words, if you were aboard a spaceship traveling near light speed, hours for you might stretch into years for someone remaining on Earth. The faster you go, the more pronounced the effect becomes, a startling truth confirmed by precise measurements with atomic clocks and high-speed particles in accelerators. Consider a calm thought experiment. Imagine a twin named Lena remaining on Earth, tending to a quiet garden, while her sibling Taro embarks on a spaceship capable of near-light speed travel. Taro's journey may last mere months from his perspective, but upon returning, Lena has aged decades. Taro steps back onto Earth, younger than his twin, a living, breathing paradox of time. This is not fantasy. It is a direct consequence of the universe's architecture, a subtle truth of space-time that touches every particle and every heartbeat. Time dilation is also influenced by gravity, a phenomenon predicted in Einstein's general relativity. The stronger the gravitational field, the more slowly time passes relative to a distant observer. This effect has been measured near massive objects like Earth itself, and even more so near neutron stars or black holes. Imagine hovering near the event horizon of a black hole. The immense gravity stretches time, so that while moments pass for you, centuries could unfold for observers far away. Time bends gently, inexorably, according to mass and motion. This interplay between speed and gravity transforms our understanding of aging. We are accustomed to thinking of time as universal and unyielding. Our clocks, calendars, and daily routines reinforce this illusion. Yet at the scale of the cosmos, time is far from absolute. The universe whispers its subtle truth, that every motion, every gravitational field, every orbit contributes to a unique rhythm of aging. Each person, each particle, experiences time differently, though we rarely notice it in daily life. Even satellites orbiting Earth illustrate this principle. The Global Positioning System, GPS, relies on incredibly precise clocks aboard satellites moving rapidly in Earth's gravitational field. Engineers must account for both the time dilation caused by speed and the gravitational difference between the satellites and Earth's surface. Without correcting for these relativistic effects, the GPS system would drift off by kilometers each day. In this way, time dilation is not just theory. It is woven into the fabric of modern technology. Beyond technology, time dilation invites reflection. It reminds us that aging is not uniform, that the flow of moments is neither simple nor universal. It turns the quiet tick of a second into something profound, a dance between motion, mass, and the curvature of space-time. It hints at doors that might one day allow us to experience the universe differently, to stretch moments or skip ahead, even if only in the imagination. The implications for time travel are immediate yet subtle. Time dilation allows for forward travel, moving into the future faster than those left behind. A journey at near light speed would place travelers ahead in time, returning them to a world changed by decades or centuries. The mechanics of backward travel are far more complex, but even the ability to manipulate forward motion hints at possibilities once thought impossible. Through the lens of relativity, the future becomes accessible, if not fully controllable. Scientists continue to explore ways to test and measure these effects more dramatically. Particle accelerators routinely push subatomic particles to near light speeds, where their decay slows in accordance with relativistic predictions. Astronauts aboard the International Space Station experience tiny, measurable effects of time dilation, though far less dramatic than Taro's imagined journey. These small-scale confirmations reinforce the elegance of the equations. Time is flexible, real, and observable. Time dilation also challenges intuition. We tend to perceive time as fixed, flowing equally for everyone, but the universe tells a different story. Each observer carries their own clock, their own timeline, subtly warped by motion and gravity. In the grand symphony of space-time, each heartbeat, each orbit, each movement bends the rhythm of existence, creating a harmony that is never exactly the same for any two observers. Perhaps most profoundly, time dilation invites a calm awe. It encourages us to imagine a universe where aging is not a simple, uniform experience, where moments can be stretched, compressed, and experienced differently, depending on one's perspective. It allows us to see ourselves as part of a cosmic rhythm, moving through a malleable fabric that connects speed, gravity, and time itself. The universe is not rigid, but fluid. It is a river whose currents are visible only to those who learn to measure its depths. As we contemplate the possibilities, the image of Taro and Lena remains a gentle meditation, one sibling exploring distant stars, moving through time at a pace different from home, and the other remaining grounded, growing with the steady heartbeat of Earth. Their reunion is a reminder that time, though variable, is shared, a connecting thread that weaves all lives into a single tapestry. Through relativity, we glimpse a universe both vast and intimate, where every second is precious, every motion significant, and every journey through space-time a quiet miracle. Time dilation, in this sense, is the first door to time travel, not a dramatic leap into the past or a fantasy of omnipotence, but a subtle, scientifically grounded reminder that the universe is stranger and more beautiful than we imagine. By understanding it, we do not merely travel, we observe, we reflect, and we learn the true depth of time itself. Section 2. Wormholes, portals through space-time. Imagine the universe as a vast sheet of fabric, stretching endlessly in all directions. Stars, planets, and galaxies rest upon this surface, and the fabric itself curves and bends under the weight of matter. Now imagine folding this sheet so that two distant points touch, creating a shortcut, a tunnel connecting points that would otherwise be separated by immense distances. This is the essence of a wormhole, a theoretical passage through spacetime that could link distant regions of the cosmos, or perhaps even moments in time. The concept of wormholes originates from the equations of general relativity, Albert Einstein's profound theory of gravity. In 1935, Einstein and physicist Nathan Rosen proposed what came to be called the Einstein-Rosen bridge, a hypothetical tunnel linking two regions of spacetime. While these bridges arise naturally from the mathematics, they are delicate structures, vulnerable to collapse if even a single particle passes through. For decades, wormholes remained purely theoretical, mathematical curiosities appearing on blackboards, but nowhere in reality. Despite their fragility, wormholes ignite the imagination. In theory, a stable wormhole could allow instant travel across the vast reaches of the universe, or even enable a traveler to experience time differently. Step into one mouth of a wormhole near Earth and exit at a distant star system far beyond what light could traverse in the same interval. The journey would not require accelerating to near light speeds, as with traditional space travel. Instead, the traveler would move through the tunnel of space-time itself, effectively shortcutting across cosmic distances. Yet wormholes are not naturally stable. According to classical physics, the immense gravitational forces at the entrance and exit would collapse the tunnel almost instantly. To keep it open, theorists propose exotic matter, material with negative energy density that repels rather than attracts. This is no ordinary matter. It behaves oppositely to anything we experience in daily life. Negative energy could, in theory, counteract the natural tendency of the wormhole to pinch closed, creating a bridge capable of supporting a spacecraft or even a human traveler. The idea of negative energy may seem fantastical, yet subtle evidence exists in the universe. In the realm of quantum physics, phenomena like the Casimir effect suggest that negative energy densities are possible on tiny scales. Two metal plates placed extremely close together in a vacuum experience a tiny attractive force, an effect arising from fluctuations in quantum fields, a manifestation of energy behaving in ways that defy classical intuition. Could these principles be scaled up to hold open a cosmic tunnel? Perhaps, though we are far from practical applications. Wormholes also raise profound questions about time. If one mouth of a wormhole were accelerated to near-light speeds and then returned to its original position, or placed in a region of intense gravity, time would pass differently at each end. In theory, this could allow travel not just through space, but through time itself. The traveler entering the younger mouth could emerge in the past, or in a future altered by relativistic effects. Physicists call these closed time-like curves, paths through space-time where cause and effect become intricate and intertwined. Such possibilities also bring paradoxes. What if someone traveled back and altered events that led to their own journey? The infamous grandfather paradox, where a time traveler could prevent their own existence, challenges our understanding of causality. Some solutions suggest that the universe protects itself, making backward time travel impossible, or constraining it in ways that preserve consistency. Stephen Hawking called this the chronology protection conjecture, hypothesizing that fundamental physical laws prevent paradoxical time loops from forming. Beyond time travel, wormholes could also illuminate mysteries of the cosmos. Imagine linking two distant galaxies, allowing instantaneous communication or exploration across unimaginable distances. They might even provide a pathway to study the far reaches of space without waiting for centuries of conventional travel. In a poetic sense, wormholes represent the universe's hidden shortcuts, the silent passages that connect the cosmos in ways we can barely perceive. In fiction, wormholes appear as portals, gateways, or even sentient entities, but the science behind them is grounded in mathematics. Computer simulations show that if a wormhole could exist, it would curve light, bend matter, and create subtle distortions in space that might be detectable. Scientists have proposed observing gravitational lensing, or the way light bends around massive objects, to search for natural wormholes. Though no definitive evidence exists yet, the search itself reflects humanity's desire to glimpse the hidden architecture of the universe. Wormholes also inspire reflection on scale and perception. The universe is vast, seemingly infinite, yet its geometry allows for elegant shortcuts. What appears insurmountable from one perspective may be traversed easily from another. In this sense, wormholes are metaphors as much as physics, reminders that the limits we perceive are often a matter of perspective, and that nature's structures may hold surprises that defy ordinary intuition. Even if we never build a wormhole or pass through one ourselves, the concept reshapes our understanding of space and time. It invites us to see the universe not as a rigid expanse, but as a flexible, interwoven fabric. Every star, every planet, every particle contributes to a dynamic cosmic tapestry in which distances and durations are not absolute, but part of an intricate geometry. Wormholes whisper the possibility that reality is richer than our senses perceive, and that the universe may contain hidden passages waiting to be discovered. Quiet, unseen, yet profoundly consequential. To imagine a wormhole is to step into calm contemplation. One can picture the tunnel stretching across darkness, a corridor of light bending gently through space. A traveler might glide through silently, feeling the pull of gravity in unfamiliar ways, emerging somewhere entirely new, or perhaps in a different time, a future or past shimmering with potential. In this meditation, wormholes are not merely theoretical constructs. They become symbols of possibility, elegance, and the profound flexibility of the universe. In this quiet, reflective sense, wormholes remind us that the universe is far stranger, more intricate, and more beautiful than our daily perceptions allow. They are doors that may never open physically. Yet they expand our imagination, inviting us to explore, to question, and to marvel at the hidden pathways of reality itself. Section 3. Black Holes and Time Loops, Nature's Extreme Laboratories. Among the most mysterious and mesmerizing objects in the cosmos are black holes, regions of spacetime where gravity becomes so intense that nothing, not even light, can escape. For centuries, they existed only in theory, mathematical predictions emerging from Einstein's general relativity. Today, we have observed their shadows, detected the ripples of their collisions in gravitational waves, and glimpsed the phenomena occurring at their event horizons. Yet beyond their enigmatic surfaces lies a deeper, almost philosophical question. Could black holes serve as natural laboratories for exploring time itself? Black holes arise when massive stars exhaust their nuclear fuel and collapse under their own gravity. As they shrink, their density grows infinitely large at a point known as the singularity, where the known laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which information cannot return to the outside universe. The space near a black hole is dramatically warped, stretching and curving the fabric of space-time to extreme degrees. This extreme curvature has profound effects on time. According to general relativity, the stronger the gravitational field, the slower time passes relative to distant observers. This phenomenon, known as gravitational time dilation, means that an astronaut hovering near the edge of a black hole would experience seconds while years pass far away. The black hole, in effect, becomes a doorway into the future, a natural time accelerator where aging slows and moments stretch. The thought of entering such a realm is both exhilarating and humbling. Imagine approaching a black hole gently, moving closer to the event horizon. The universe outside seems to speed up, stars whirling faster, galaxies spinning more quickly. Yet for the traveler, every movement feels normal, a profound reminder that time is not universal, but relative, shaped by gravity and motion. In this way, black holes are not just destructive forces, they are cosmic laboratories, revealing the intimate connection between space, time, and gravity. Some theorists had extended this idea further, contemplating rotating black holes, or Kerr black holes, which possess not only mass but angular momentum. Unlike non-rotating black holes, Kerr black holes create regions called ergospheres, where space-time itself is dragged along with the rotation. This frame-dragging effect means that paths through space and time are twisted, opening the possibility of closed time-like curves, theoretical loops where a traveler could, in principle, journey backward in time. These loops, sometimes called time loops, suggest that nature itself might contain corridors for moving through time, at least in extreme conditions. They are highly speculative and fraught with paradoxes, yet they emerge naturally from Einstein's equations. Within the mathematics of a Kerr black hole, one finds that spacetime is not only curved but entwined, creating possibilities where past, present, and future intersect in ways that defy everyday intuition. Of course, reality imposes limits. The intense gravity near a black hole's singularity would stretch and compress any matter attempting to enter, a process known as spaghettification. No human or spacecraft could survive intact. The mathematics may allow time loops, but the physical experience remains lethal. Black holes, then, are both tantalizing and terrifying, cosmic teachers showing us the extremes of spacetime, even as they remain inhospitable to life as we know it. Yet there are subtler, safer ways to observe their temporal effects. Satellites orbiting compact stars, neutron stars, and smaller black holes can measure time dilation indirectly. Observations of pulsars orbiting black holes reveal tiny discrepancies in timing that align precisely with predictions from general relativity. These natural experiments, conducted across the vast darkness of space, confirm that time's flow is flexible, not absolute, and that gravity can bend it in astonishing ways. Black holes also provide insight into the limits of physics. At the singularity, quantum mechanics and general relativity clash, leaving a mystery that may hold the key to understanding time itself. Could a quantum theory of gravity resolve paradoxes? Could wormholes naturally form within certain black holes, connecting distant regions of space-time? The questions are profound, and answers remain elusive. Yet the very presence of these possibilities invites awe, curiosity, and calm reflection, an awareness that the universe is richer, stranger, and more interconnected than we can easily imagine. In addition to their temporal effects, black holes remind us of the subtle interplay between observation and reality. The passage of time near a black hole is not just a local phenomenon. It affects what distant observers perceive. A falling star might appear to freeze at the event horizon, its light stretching into a ghostly, red-shifted trail. From the outside, time seems to halt. For the star itself, the fall continues inexorably. In this duality, black holes teach a quiet lesson. Reality is relative, dependent on perspective, and layered with hidden depths. Ultimately, black holes serve as nature's extreme laboratories, demonstrating that time is not fixed, but malleable, that the universe contains regions where moments stretch and loops may form, and that the cosmos is far more intricate than the clockwork of daily life suggests. They invite calm contemplation, the quiet acknowledgement that even in darkness, the universe pulses with possibility, and that the laws governing time are as elegant as they are mysterious. To consider a black hole is to consider the fluidity of time itself. They are silent witnesses to cosmic history, engines of transformation, and gateways to understanding. Though we may never venture physically into their depths, their existence encourages us to imagine, to wonder, and to reflect on the hidden symphony of space-time. Here, in the shadow of the black hole, time is not a river flowing in one direction. It is a landscape to explore, a secret of the universe waiting to be understood, a meditation on the profound connection between gravity, motion, and the very essence of reality. Section 4. Cosmic Strings, Threads of Time. In the silent depths of the cosmos, far beyond the reach of our eyes, theoretical filaments of unimaginable density may stretch across the universe, cosmic strings. These are not threads in the familiar sense, nor are they made of any material we know. Instead, cosmic strings are hypothesized one-dimensional defects in space-time itself, relics from the early universe, formed fractions of a second after the Big Bang. Though invisible, their influence could ripple across space and time, bending reality in ways both subtle and profound. Imagine space-time as a vast, flexible fabric. Cosmic strings are like infinitesimally thin cracks or seams, infinitely dense along their length. A string thinner than an atom could carry the mass of a mountain or even a planet per centimeter. Their gravitational pull is unlike anything we encounter in daily life. Rather than attracting in the familiar way, a cosmic string would warp space so severely that moving around it could create loops, unusual pathways, and distortions that defy ordinary intuition. One of the most intriguing possibilities of cosmic strings lies in their potential to warp time. The intense gravitational field around a string could bend space-time to such a degree that closed time-like curves might emerge. These are pathways where time loops back on itself, theoretically allowing travel to the past. Unlike wormholes, which require exotic matter to remain open, cosmic strings might naturally create regions where time itself folds, simply due to their immense tension and density. To envision this, picture moving near two parallel cosmic strings, set in motion at near light speed. The space-time between them becomes twisted. An object traveling carefully along this corridor might trace a path that loops backward in time. While this remains entirely theoretical, it demonstrates that the universe could harbor natural structures capable of extraordinary effects on the flow of time. It is a humbling thought. Threads of reality, invisible and immense, silently influencing the passage of moments. Cosmic strings are not merely abstract. They emerge naturally from certain grand unified theories in physics, which attempt to merge the fundamental forces of nature into a single framework. In these models, as the universe cooled from its initial fiery state, imperfections could form, leaving behind linear defects, cosmic strings. Though extremely rare, their existence would help explain subtle irregularities in the cosmic microwave background, the faint afterglow of the Big Bang, and might even provide clues to the universe's early evolution. Observationally, detecting a cosmic string would be a delicate endeavor. They are invisible to light and matter, yet their gravitational effects could bend light, creating subtle distortions in the appearance of distant stars or galaxies. This phenomenon, known as gravitational lensing, is similar to the bending of light by massive galaxies or black holes, but in a uniquely linear pattern. Scientists have proposed looking for these telltale signs as a means of confirming the existence of cosmic strings. The cosmos may thus be silently threaded with relics of its own creation, whispering secrets from the dawn of time. Cosmic strings also offer a window into philosophical reflection. They remind us that the universe is not simply a collection of stars and galaxies, but a living tapestry of hidden structures, many invisible yet profoundly influential. Like threads in a grand cosmic fabric, they hold space and time together, subtly shaping the trajectories of planets, the paths of light, and potentially even the flow of history itself. The universe is not flat or uniform. It is textured, folded, and layered, with hidden corridors waiting for discovery. The connection between cosmic strings and time travel, though speculative, is both elegant and inspiring. While the concept of wormholes requires exotic matter, and black holes present near insurmountable hazards, cosmic strings offer a natural, albeit elusive, pathway. The equations suggest that under the right conditions, Traveling near these threads could allow one to loop in time, a quiet and almost serene dance with the flow of moments. Beyond their theoretical applications, cosmic strings provoke awe simply by their scale and density. To imagine a filament thinner than a proton, yet carrying the mass of a planet, stretches the mind. Their presence, if real, would serve as a reminder that the universe contains extremes far beyond ordinary experience, yet governed by the precise and beautiful language of mathematics. They are subtle sculptures of space-time, silent, invisible, and enduring for billions of years. Even in absence of direct observation, cosmic strings invite meditation on the nature of time itself. If time is influenced by gravity, speed, and curvature, then these linear structures become more than cosmic relics. They are threads along which reality might fold and bend. They hint at the universe's quiet complexity, where cause and effect, past and future, are not fixed, but pliable, waiting for those who understand the rules of the fabric. In contemplating cosmic strings, one finds both humility and wonder. The universe may be threaded with invisible highways, looping pathways, and latent corridors of time. These are not playgrounds for immediate exploration, but they stretch the imagination, suggesting that time travel, while currently beyond our reach, may be embedded in the very geometry of space-time. It is a gentle, profound reminder. Reality is layered, hidden in subtle folds, and far stranger than the surface we perceive. And so, cosmic strings remain threads of possibility. They are whispers from the early universe, hints that space and time are malleable, and that the cosmos may contain secrets beyond our senses. Though unseen, they shape the universe, and perhaps the very flow of moments themselves, inviting quiet reflection on the elegance, mystery, and infinite complexity of the cosmos. Section 5. The Grandfather Paradox and the Logic of Time Travel. Time travel captures the imagination not only because it defies the flow of ordinary experience, but because it challenges the very logic of cause and effect. Among the most famous conceptual puzzles in this realm is the Grandfather Paradox, a thought experiment that asks us to confront what happens if a traveler moves backward in time and alters events that led to their own existence. It is a paradox that blends physics with philosophy, a quiet meditation on the fragility of causality. The paradox is simple to state, yet profoundly unsettling. Imagine a person traveling into the past, visiting a time when their grandfather was young, before the birth of their parent. If they inadvertently or deliberately prevent their grandfather from meeting their grandmother, the traveler would never be born. Yet if the traveler were never born, how could they have gone back in time to prevent the meeting? The sequence of cause and effect collapses into contradiction, a knot of impossibility that seems to defy logic. Philosophers and physicists alike have pondered this conundrum. One perspective is that the universe might forbid paradoxical events. Stephen Hawking, for example, proposed the chronology protection conjecture, suggesting that fundamental physical laws prevent closed time-like curves, the loops in time necessary for backward travel, from forming in such a way that paradoxes could occur. In this view, time might allow forward travel through relativistic effects, but true interference with the past may remain impossible. The universe preserves its own consistency, quietly enforcing order within the apparent chaos of potential time travel. Yet other interpretations are equally fascinating. The many worlds hypothesis, rooted in quantum mechanics, offers a different resolution. According to this view, traveling to the past does not alter the original timeline, but instead creates a branching universe, a parallel reality where the traveler's actions unfold independently. In this scenario, preventing a grandfather from meeting a grandmother does not erase the traveler's existence in the original timeline. It simply generates a new, alternative history. Paradox disappears, replaced by a multiverse in which every possibility is realized somewhere. The idea is profound and serene in its way. The universe is not singular and rigid, but expansive, layered, and infinitely branching. Even if paradoxes can be circumvented theoretically, they highlight the subtle relationship between time, choice, and causality. Our understanding of events as linear, a sequence of causes leading inexorably to effects, is an approximation useful for everyday life, but incomplete in the extreme physics of space-time. A universe that allows backward paths must also confront constraints, feedback loops, and the preservation of self-consistency. The mathematics suggests that even if time loops exist, they are tightly constrained, avoiding logical contradictions while permitting remarkable distortions of sequence. Consider the implications for travelers. A journey into the past might feel perfectly normal, yet the universe could be silently nudging events to prevent paradox. Perhaps a seemingly trivial accident, a delayed encounter, or a subtle miscalculation ensures that the traveler cannot disrupt essential outcomes. The idea that physics might protect the timeline is both comforting and mysterious. It hints at a universe that is self-regulating, quietly preserving coherence even amid profound distortions in space and time. The grandfather paradox also encourages reflection on human perception of time. We tend to view past, present, and future as separate and sequential. Yet physics suggests a more flexible reality, where time is a dimension, malleable and intertwined with space. The paradox emerges only when we impose our intuitive linear perspective on a universe governed by relativity and quantum uncertainty. By stepping back, we realize that the challenges of backward time travel are as much about perspective as about fundamental laws. Interestingly, these philosophical considerations intersect with real scientific inquiry. Physicists exploring wormholes, cosmic strings, or black holes must consider self-consistency to determine whether closed time-like curves could exist without creating contradictions. Calculations reveal that certain configurations allow loops that respect causality, while others collapse under the weight of paradox. Even in the abstract equations, the universe appears to favor coherence, subtly guiding the logic of events even when the paths of time bend and fold. The paradox also evokes quiet contemplation of responsibility and choice. Traveling through time, altering events, or even glimpsing the past invites questions about ethics and consequence. Could one intervene in history without unintended effects? Would every action ripple outward, creating subtle shifts across space-time? These considerations mirror the care with which we navigate life itself. Small actions, even unseen, shape the broader flow of events. In this sense, the paradox is a metaphor for the interconnectedness of reality, reflecting both physics and human consciousness. Ultimately, the grandfather paradox is less a problem to solve than a lens through which to explore the nature of time and logic. It teaches that time is flexible yet constrained, imaginative yet disciplined. The universe allows extraordinary possibilities, but it enforces coherence in ways that preserve its integrity. To contemplate the paradox is to meditate on the balance between freedom and limitation, chance and order, possibility and consequence. In reflecting on the grandfather paradox, one begins to see time not as a rigid arrow, but as a subtle, interconnected web. Each moment, each action, each choice threads into the tapestry of space-time, where the past and future influence one another in ways that are often hidden yet deeply significant. The universe, in its quiet elegance, contains safeguards, rules, and patterns that maintain harmony even when our imagination envisions loops, leaps, and journeys across centuries. The paradox reminds us that the journey through time is as much an intellectual and philosophical exploration as a physical one. It encourages calm, patient reflection, a recognition that reality is layered, paradoxical, and awe-inspiring. Time travel, whether through wormholes, relativistic journeys, or theoretical loops, becomes more than science. It becomes a meditation on the subtle, intricate structure of the cosmos. Section 6. Time Travel and the Quantum Realm. Uncertainty and Possibility. As we journey deeper into the mysteries of time, we find ourselves entering the delicate, often counterintuitive world of quantum mechanics. Here, the universe behaves in ways that challenge ordinary experience, and where the rules of cause and effect are subtle, probabilistic, and layered with uncertainty. Quantum mechanics does not only govern the infinitesimal particles of the cosmos, it also offers profound insights into the possible nature of time itself. In classical physics, the past leads to the present, which in turn leads to the future, in a neat, predictable sequence. But in the quantum realm, particles exist in superpositions, simultaneously occupying multiple states until measured. An electron may spin both up and down. A photon may traverse two paths at once. The universe at this scale is probabilistic, fluid, and interconnected. When combined with the flexible geometry of spacetime described by relativity, these principles suggest tantalizing possibilities for the flow of time. Consider the idea of quantum tunneling, where particles can cross barriers that would be insurmountable in classical physics. In a metaphorical sense, time itself might contain similar barriers, with quantum effects allowing subtle excursions through temporal dimensions. While the macroscopic world seems rigid and sequential, the microscopic world whispers that reality may be far more flexible than our senses perceive. The probabilistic nature of quantum events opens a door to imagining pathways through time that are normally hidden or forbidden. Quantum mechanics also introduces the concept of entanglement, where particles separated by vast distances share states instantaneously. Measurement of one instantly influences the other, a phenomenon Einstein famously called spooky action at a distance. Entanglement suggests that correlations in the universe exist independently of classical temporal sequences. If time is intertwined with space, as relativity indicates, then entanglement hints at deeper connections that may subtly influence the order of events, a faint echo of time's pliability at the smallest scales. Some theorists have proposed that quantum mechanics might provide mechanisms for stabilizing wormholes or even permitting time loops without violating causality. In these models, quantum fluctuations, the transient appearance of energy and particles in empty space, could prevent a wormhole from collapsing. Negative energy, essential to keep the tunnel open, may arise naturally from quantum effects. The mathematics is intricate, and practical applications remain far beyond our current technology. Yet the possibility exists in principle. The quantum world may gently support structures that allow temporal exploration. Moreover, quantum uncertainty challenges our conventional notions of determinism. In a classical universe, knowing the state of every particle allows, in theory, prediction of the future. In a quantum universe, uncertainty is fundamental. The Heisenberg principle tells us that certain pairs of properties, like position and momentum, cannot both be known with absolute precision. Applied to time, this principle implies that the universe may not be a rigid clockwork, but a landscape of probabilities. Time travel, in this sense, may not be about fixed outcomes, but about navigating a web of potential histories. This probabilistic nature of the quantum realm also interacts with the concept of parallel universes. If every quantum choice generates a branching reality, then journeys through time may create alternate timelines rather than altering a single past. Such ideas align with the many worlds interpretation, providing a graceful solution to paradoxes like the grandfather paradox. The universe, from a quantum perspective, is less a straight line and more a branching tree, with each choice and fluctuation opening new possibilities. Even if we cannot yet traverse these quantum pathways, contemplating them offers a calm, meditative perspective. Quantum time is subtle, flexible, and interconnected. It reminds us that our everyday perception of seconds, minutes, and hours is only an approximation, a coarse-grained view of a more intricate, layered reality. The universe at its smallest scales is alive with potential, weaving the past, present, and future into a subtle dance of probabilities. Time travel in the quantum realm also invites philosophical reflection. If particles can exist in multiple states, if events are not strictly deterministic, then perhaps the boundaries between past, present, and future are more permeable than intuition suggests. We may not yet have the means to move through time consciously, but the universe itself experiments constantly at the smallest scales with the possibilities of temporal flexibility. In this sense, quantum mechanics transforms the cosmos into a quiet, elegant laboratory where the future and past coexist as a tapestry of probabilities waiting to be understood. Finally, contemplating the quantum world fosters a sense of humility and wonder. It reminds us that the universe is not limited to what we can see or touch, that the rules governing reality are subtle, and that even the tiniest particles contain secrets about time itself Time travel may remain theoretical, but the exploration of quantum mechanics shows us that reality is far more intricate, delicate, and beautiful than it appears at the surface. Each particle, each fluctuation, each entanglement hints at hidden pathways through the dimensions of space and time. In this quiet reflection, one realizes that time travel, at its most profound, is not merely about moving backward or forward in moments. It is about understanding the fluid, interconnected nature of the universe, where cause, effect, and possibility are entwined. The quantum realm, invisible to the naked eye, invites us to see time not as a strict river, but as a flowing, branching, and wondrous landscape, a meditation on reality, chance, and the intricate architecture of the cosmos. Section 7. Wormhole stabilization and exotic matter. Among the most fascinating ideas in theoretical physics is the concept of a traversable wormhole, a tunnel through space-time, connecting distant points or even different moments in time. The very mathematics of Einstein's general relativity permits such structures, but here, theory meets a sobering reality. A wormhole, left to the forces of the universe, would collapse the instant anything attempted to pass through. For a wormhole to become a doorway rather than a fleeting mathematical curiosity, it must be stabilized. The solution, tantalizingly, may lie in exotic matter, an unusual form of energy that behaves in ways counterintuitive to our everyday experience. To appreciate the challenge, consider the nature of a wormhole. In relativity, space-time is like a flexible fabric. A wormhole forms when this fabric bends to create a tunnel, a shortcut connecting two distant points. However, the natural curvature of space-time tends to pinch the tunnel closed under the influence of gravity. Imagine pressing on a flexible straw from both ends. Without support, the walls collapse. A traversable wormhole faces an analogous problem. The gravitational forces trying to crush it are immense. Ordinary matter, which only attracts, cannot hold it open. Here, exotic matter enters the scene. Exotic matter is a theoretical form of matter with negative energy density. Unlike the matter we encounter daily, which pulls objects together, negative energy pushes space-time outward. This repulsive property could counteract the collapse of a wormhole, stabilizing the tunnel long enough for a spacecraft, or even information, to traverse it safely. It is not science fiction, but a natural prediction of certain solutions to Einstein's equations, combined with phenomena observed in the quantum world. In other words, exotic matter may already exist in subtle forms, waiting to be harnessed in theory, if not in practice. The quantum world provides intriguing hints. Effects like the Casimir effect demonstrate that negative energy can arise between closely spaced metal plates. In a vacuum, quantum fluctuations create tiny pressures that push the plates together, effectively demonstrating negative energy densities on a minuscule scale. While far from the magnitude required to hold open a macroscopic wormhole, these experiments confirm that negative energy is not purely hypothetical. The universe, in its subtle mechanics, allows for forms of energy that defy classical intuition. Stabilizing a wormhole is not merely about inserting exotic matter. The distribution of negative energy must be precisely arranged along the tunnel to counteract gravitational forces without destabilizing the surrounding spacetime. Calculations suggest that even minor misalignments could cause the wormhole to pinch or collapse violently. The engineering challenges, if such a task were ever attempted, would be staggering. Yet the mathematics offers reassurance. In principle, a stable, traversable wormhole is possible, a testament to the elegance of general relativity. Theoretical models also suggest that wormhole stabilization may allow for controlled manipulation of time flow. If one mouth of a wormhole is accelerated to near light speed or placed in a region of strong gravitational potential, relativistic effects can cause time to pass differently at each end. A traveler entering the younger mouth could emerge in a different temporal frame than the starting point, creating a pathway for forward or backward time travel. Exotic matter, by keeping the tunnel open, becomes the silent enabler of these extraordinary possibilities. Despite the promise, the concept raises profound physical and philosophical questions. Negative energy is exotic precisely because it is rare and counterintuitive. How much is needed? Can it exist in sufficient quantities? And even if the tunnel is stabilized, what are the consequences of passing through? Radiation, tidal forces, and interactions with the surrounding spacetime could pose hazards. The mathematics hints at possibility, but the universe imposes caution. Nature allows for wonder, yet with delicate constraints. Wormhole stabilization also encourages reflection on the interconnectedness of physics. Concepts from general relativity, quantum mechanics, and cosmology converge in this endeavor. Quantum fluctuations may provide negative energy. Relativity defines the tunnel's curvature, and cosmology sets the large-scale context in which such structures might exist. The universe operates as an intricate symphony, each principle harmonizing with others, revealing pathways that are mathematically possible, even if experimentally elusive. Beyond the technical challenges, wormholes provoke a meditative perspective on reality. To imagine a tunnel through space-time stabilized by negative energy is to envision a universe far more flexible and intricate than our daily perceptions suggest. Time is not a rigid arrow. Space is not a uniform expanse. Instead, reality is a dynamic, layered fabric with potential corridors of motion hidden within its geometry. Wormholes, in this sense, become symbols of possibility, reminders that the universe contains structures and relationships that exceed our immediate senses. Some theorists speculate further about the energy requirements for macroscopic wormholes. Early calculations suggest that enormous amounts of negative energy, perhaps comparable to the mass energy of a star, would be needed to hold open a tunnel large enough for a human or spacecraft. The challenge is not only technological, but conceptual. Creating, manipulating, and sustaining exotic energy in quantities sufficient for stabilization stretches imagination to its limits. Yet the fact that the equations allow it at all is a quiet triumph of human understanding. an acknowledgement that the universe is not bound by simplicity alone. Even if practical wormhole travel remains far beyond reach, the concept enriches our understanding of the cosmos. It reminds us that physical laws are not merely constraints, but frameworks for extraordinary phenomena. Exotic matter and wormhole stabilization illuminate the subtle balance between attraction and repulsion, gravity and geometry, energy and space. The universe becomes a place of elegance, where the extraordinary is embedded in the very equations that govern reality. Finally, contemplating stabilized wormholes offers a serene reflection on time, space, and human curiosity. These tunnels, hypothetical though they are, serve as portals not only through space-time, but through imagination. They invite us to meditate on the hidden structures of reality, to appreciate the universe's intricate dance, and to recognize that possibility exists even where the limits seem absolute. Exotic matter is not just a theoretical tool, it is a symbol of the subtle, hidden mechanisms that allow the cosmos to stretch, fold, and echo across space and time. In the quiet consideration of wormhole stabilization, one senses the calm wonder of the universe itself, precise, intricate, and unexpectedly flexible. Negative energy holds more than a tunnel open. It holds a window to the imagination, a vision of the cosmos where time and space are not rigid, but alive, interwoven, and full of possibilities yet to be discovered. Section 8. Time Machines and Practical Constraints. The dream of constructing a time machine has long captured the human imagination. From science fiction tales to serious theoretical research, the concept evokes wonder, curiosity, and even a gentle sense of trepidation. In the realm of physics, however, the idea is both tantalizing and deeply constrained. While equations suggest that time travel might be possible under certain extreme conditions, practical realities, from energy requirements to stability concerns, impose formidable limits. Time machines, in theoretical terms, often rely on closed, time-like curves, pathways through space-time that loop back on themselves. These curves appear in the mathematics of general relativity when space is warped in precise ways, such as near rotating black holes, cosmic strings, or traversable wormholes. A traveler following a closed time-like curve could, in principle, return to an earlier moment, creating the possibility of backward time travel. Yet the construction of such a machine is far more complicated than simply connecting 2 points in space. One of the most significant constraints is energy. Maintaining the extreme warping of space-time necessary for a traversable time machine would require vast amounts of energy, far beyond anything currently achievable. Negative energy, or exotic matter, which is needed to stabilize wormholes or prevent collapse, must be concentrated in precise configurations. Even tiny deviations could destabilize the system, collapsing the tunnel or creating dangerous distortions. The universe, in its elegance, demands balance. A time machine is theoretically possible only when every element is perfectly aligned. Another challenge lies in causality. Time machines that allow travel to the past risk creating paradoxes, such as the grandfather paradox. where a traveler could prevent their own existence. While some models, such as the many worlds interpretation, provide conceptual solutions, the practical consequences remain uncertain. Physicists must ensure that the design of any theoretical machine preserves the logical consistency of events, a subtle and profound constraint that transcends engineering. Time travel is not merely a technical challenge, it is a negotiation with the very structure of reality. The stability of a time machine also presents profound difficulties. Traversable wormholes, often proposed as potential machines, are naturally unstable. They collapse under ordinary gravitational influences unless stabilized by negative energy. Even if a wormhole could be held open, it would be sensitive to tidal forces, radiation, and quantum fluctuations. Navigating such a passage would require precise calculations and delicate control, as any misstep could have catastrophic consequences. The cosmos allows these structures in principle, but in practice, they demand a level of control far beyond current technology. Moreover, time machines raise subtle questions about interactions with the environment. Any passage through a closed time-like curve could create ripple effects in spacetime, influencing matter and energy along the path. Even small disturbances might propagate, producing unforeseen consequences. The universe behaves not only according to local laws, but also as a web of interdependent relationships. A time machine is not isolated. It interacts with the cosmos, and these interactions must be considered in any theoretical design. Despite these formidable constraints, imagining time machines remains a valuable exercise. It pushes the boundaries of physics, encourages exploration of extreme environments like black holes and wormholes, and deepens our understanding of the universe's flexibility. In contemplating such devices, we engage with the most fundamental questions. What is time? How rigid or malleable is the flow of events? What structures does the universe permit, even if only mathematically? The thought experiment itself becomes a meditation, revealing the elegance of physical laws and the creativity of the human mind. The pursuit of time machine concepts also illustrates the interplay between theory and imagination. Equations alone cannot fully capture the experience of navigating warped spacetime. Thought experiments, visualization, and careful reflection allow scientists and enthusiasts alike to explore possibilities, consider consequences, and grasp the subtle mechanisms underlying reality. In this way, the idea of a time machine is as much about understanding the cosmos as it is about building devices. It trains the mind to perceive space and time as fluid, interconnected, and rich with hidden pathways. Interestingly, these explorations reveal that the universe itself may contain natural time machines. Rotating black holes, cosmic strings, and even quantum effects could create conditions where closed time-like curves exist, at least temporarily, without human intervention. These cosmic laboratories, though extreme and inhospitable, demonstrate that time travel is not purely fictional. The laws of physics allow structures that bend the flow of events, suggesting that the universe, in its quiet elegance, is far more flexible than our everyday experience suggests. Practical constraints, however, remain decisive. Even if natural pathways exist, accessing them safely is a different matter. Extreme gravitational forces, tidal effects, and energy demands make such journeys perilous. The mathematics describes possibility, but reality imposes safety, energy, and stability as unyielding requirements. A time machine may remain forever a thought experiment, a beautiful intersection of imagination and physical law, rather than a tangible device. In reflecting on time machines, one also encounters a quiet philosophical lesson. These theoretical constructs remind us that the universe is not a rigid clockwork, but a flexible, interwoven fabric. Space and time are not merely coordinates. They are dynamic, sensitive to energy, motion, and curvature. The concept of a machine that traverses this fabric invites awe, humility, and a deep sense of wonder. Even the limitations themselves, the energy requirements, the stability concerns, the paradoxes, reveal the intricate balance and profound intelligence of cosmic law. Ultimately, contemplating time machines is less about engineering than about perspective. It is about recognizing that the cosmos allows pathways beyond immediate perception, that time can be stretched, looped, or warped under extreme conditions, and that even the most fantastical ideas can teach us about the hidden structure of reality. In this meditation, the time machine becomes a symbol of possibility, reminding us that the universe is vast, intricate, and far more mysterious than everyday experience suggests. Section 9. Observational evidence and searches for time warps. While time travel remains theoretical, the universe provides subtle hints of its malleable nature through observable phenomena. Astrophysicists and cosmologists have long searched for time warps, distortions in space-time that could illuminate the interplay of gravity, motion, and temporal flow. These investigations are not attempts to create time machines, but rather careful, patient studies of nature's most extreme and fascinating environments. The results reveal a cosmos more intricate, fluid, and quietly extraordinary than we might imagine. One avenue of exploration involves gravitational lensing, a phenomenon predicted by Einstein's general relativity. Massive objects, such as galaxies or black holes, bend the path of light passing nearby, creating arcs, rings, or multiple images of distant stars. In essence, light itself is forced to take longer paths through warped space-time, arriving at Earth slightly delayed. While this is not time travel in the conventional sense, it demonstrates the tangible effects of space-time curvature on the perception of time and distance. The universe, in its subtle mechanics, allows us to witness the bending of moments and light simultaneously. Astronomers also study pulsars, orbiting compact objects, such as neutron stars and black holes. Pulsars emit remarkably regular pulses of radio waves, acting as cosmic clocks. By observing deviations in pulse timing caused by strong gravitational fields, scientists can measure gravitational time dilation directly. This is the same effect that would slow a traveler's clock near a black hole or a highly warped wormhole entrance. These observations offer a natural laboratory for testing the principles underlying potential time travel, illustrating that the universe itself can bend and stretch temporal flow in ways both predictable and awe-inspiring. Beyond individual stars, researchers examine cosmic strings and other hypothesized relics from the early universe. These one-dimensional defects, if they exist, would warp spacetime along their length, potentially creating closed, time-like curves. While no definitive evidence for cosmic strings has been found, scientists continue to analyze the cosmic microwave background for subtle distortions or unusual lensing patterns. Each observation, whether confirming or constraining theories, refines our understanding of how extreme mass and energy could twist time itself. Black holes remain central to the search for natural time warps. Observations of matter spiraling into supermassive black holes reveal effects predicted by relativity. Time slows near the event horizon. Light becomes redshifted, and the orbits of nearby stars deviate from Newtonian predictions. In some cases, high-resolution imaging has captured the shadow of a black hole, providing empirical evidence that space-time is not uniform but profoundly curved. Here, the universe displays its flexibility, reminding us that the flow of time is sensitive to gravity, motion, and mass in ways that transcend ordinary perception. Gravitational waves, ripples in the fabric of space-time, generated by the collision of massive objects, offer another observational window. Detected for the first time in 2015 by LIGO, these waves demonstrate that space-time is dynamic and responsive, capable of transmitting distortions across vast cosmic distances. Each wave carries subtle information about the curvature and motion of space-time, revealing that time itself is embedded in a responsive, oscillating medium. The universe, in this sense, is not static, but alive with motion, bending, and rhythm, a natural theater for the possibilities suggested by time travel theories. Researchers also investigate high-energy astrophysical events such as gamma-ray bursts and supernovae, which occur under extreme gravitational and energetic conditions. Observing the timing, intensity, and light paths of these events allows scientists to test predictions about relativistic effects, including time dilation and energy momentum relationships. While these observations do not allow travel through time, they confirm that the flow of time is relative, dependent on local conditions, and capable of subtle distortions under extreme circumstances. Even speculative searches for wormholes rely on careful observation. Some scientists propose looking for unusual gravitational lensing effects, sudden energy emissions, or peculiar motion of stars that could indicate a tunnel through space-time. Though no definitive wormhole has been observed, the search itself illuminates the remarkable capacity of modern instruments and analysis methods to detect the faint fingerprints of extreme physics. The universe may hold structures invisible to our eyes, yet accessible to patient observation and reasoned inference. These searches collectively reveal a quiet lesson. The universe is layered and dynamic, filled with hidden corridors where time behaves in unusual ways. While humans may not yet traverse these corridors physically, studying them expands our comprehension of reality. Each observation, each subtle distortion, demonstrates that time is not fixed, but woven into the very fabric of space-time, responsive to mass, motion, and energy. The cosmos encourages both curiosity and humility, offering glimpses of what might be possible without violating known laws. Finally, the pursuit of time warts emphasizes the interconnectedness of science and imagination. Observational astronomy provides empirical constraints. Theoretical physics offers conceptual frameworks. Together, they guide us in exploring the universe's hidden dimensions. The act of searching, of observing, measuring, and contemplating becomes itself a meditation on the elegance and subtlety of space-time. Even the absence of definitive evidence speaks to the precision and rigor of scientific inquiry, a quiet affirmation that the universe rewards patience, curiosity, and careful reflection. In this way, the search for time warts is not a quest for practical time travel, but a journey into understanding. Each lensing arc, each pulse from a distant star, each gravitational wave whispering across the void reminds us that time is flexible, relational, and full of mystery. The universe is both ordered and astonishingly malleable, inviting us to perceive it with patience, wonder, and reverence. By looking outward, we glimpse the hidden architecture of moments themselves, discovering that the cosmos contains corridors of possibility far beyond ordinary experience. Section 10. Temporal Paradoxes and Quantum Consistency. The concept of time travel, as exhilarating as it is, inevitably raises profound questions about cause and effect. Traveling backward in time could lead to temporal paradoxes, situations where the chain of events contradicts itself, challenging the logic of reality. One of the most famous examples, the grandfather paradox, asks what would happen if a traveler prevented their own existence. While such paradoxes are mind-bending, the quantum world offers elegant possibilities for maintaining consistency in the fabric of time. At the heart of this discussion is the nature of quantum mechanics. Unlike the classical universe, where events unfold in a rigid sequence, the quantum realm is probabilistic. Particles exist in superpositions, capable of multiple states simultaneously, and only upon measurement do they collapse into definite outcomes. This inherent uncertainty provides a mechanism for resolving paradoxes. Rather than altering a fixed past, a time traveler's actions may simply select one among many possible histories, preserving consistency without contradiction. One theoretical framework that addresses temporal paradoxes is the Novikov self-consistency principle. Proposed in the 1980s, it states that any event occurring along a closed time-like curve must be self-consistent. In other words, actions taken by a traveler in the past cannot produce contradictions. The universe enforces its own logic. If a traveler attempts to prevent a grandfather from meeting a grandmother, something, a twist of circumstance, a chance accident, ensures that the timeline remains intact. The cosmos, in this view, becomes a careful, patient guardian of consistency, balancing freedom with order. Quantum mechanics deepens this understanding through the concept of many worlds branching. Each quantum choice generates an alternative universe, a new branch in the multiverse. If a traveler interferes with the past, they may create a new timeline while leaving the original unchanged. Paradoxes dissolve because there is no single fixed past to disrupt. All possibilities exist somewhere in the vast, branching tapestry of reality. This view transforms the universe from a rigid sequence into a dynamic, layered structure, where time is as fluid and multidimensional as the imagination allows. Even within a single timeline, quantum effects provide subtle tools for maintaining coherence. The probabilistic nature of particle behavior means that certain events are inherently unpredictable, and the universe can adjust outcomes to prevent contradictions. This is not conscious intervention, but a consequence of the laws of physics themselves. The consistency of time is woven into the underlying structure of reality, embedded in the same principles that govern matter, energy, and the curvature of space-time. The interplay between relativity and quantum mechanics further illuminates these ideas. Relativity allows for closed time-like curves, while quantum uncertainty prevents paradoxes from arising catastrophically. Together, they suggest that the universe can accommodate time travel under extreme conditions, but always within a framework that preserves logical coherence. Paradoxes are not signs of failure in the laws of physics. They are hints about the subtle, self-regulating nature of space-time and probability. This perspective also invites a calm reflection on cause and consequence. Even if paradoxes are avoided, the universe emphasizes subtlety. Small actions can ripple outward in complex ways, influencing events and probabilities rather than creating outright contradictions. The cosmos is not chaotic. It is delicately balanced, where freedom exists alongside constraints, and creativity in action is harmonized with consistency in outcome. Time, then, is not merely a sequence of moments, but a living, responsive dimension. Experimental physics may one day offer indirect evidence of these principles. Observations of quantum systems, especially those entangled across space-time, could reveal hints about the universe's self-consistent behavior. While macroscopic time travel remains hypothetical, the mechanisms that prevent paradox at the quantum level are real, observable, and integral to reality's structure. By studying these effects, scientists glimpse how the cosmos maintains coherence in the face of complexity and uncertainty. Philosophically, temporal paradoxes invite contemplation of freedom, choice, and responsibility. Even in a universe that enforces consistency, actions have meaning. Every decision threads through space-time, influencing outcomes within probabilistic boundaries. The universe becomes a careful dance between possibility and necessity, where exploration, curiosity, and ethical reflection are as relevant as the equations themselves. Paradox is not merely a puzzle, but a meditation on the delicate architecture of reality. In the end, quantum mechanics offers reassurance. The universe is both flexible and orderly. Time can bend, loops may exist, and closed curves may allow backward travel, in principle. Yet the laws of physics preserve consistency, preventing contradictions and paradoxical breakdowns. Reality is not a fragile illusion, but a resilient, elegant tapestry, capable of sustaining imagination, exploration, and wonder without collapsing under the weight of impossibility. Temporal paradoxes, when viewed through this lens, are not threats but guides. They teach patience, reflection, and reverence for the subtle laws that govern the cosmos. Even in speculation, the universe appears serene, self-regulating, and full of hidden harmony. Quantum mechanics, relativity, and probability converge to create a quiet assurance. Time travel may challenge our intuition, yet the cosmos possesses the wisdom to remain consistent, coherent, and deeply beautiful. Finally, contemplating paradoxes and quantum consistency evokes a sense of humility and awe. The universe is vast, intricate, and profoundly more complex than our linear perceptions suggest. Closed time-like curves, branching timelines, and probabilistic safeguards remind us that reality is layered, flexible, and alive with possibility. Even if time travel remains beyond practical reach, the meditation on paradox, quantum mechanics, and cosmic coherence offers a profound and calming vision of the universe, a place where logic, wonder, and possibility coexist in delicate balance, quietly inviting our curiosity. Section 11. The role of black holes in time manipulation. Among the most enigmatic objects in the cosmos, black holes stand as both guardians and guides of the universe's deepest secrets. Their immense gravitational pull does more than bend space. It profoundly affects the flow of time itself. For centuries, black holes have inspired both fear and fascination, and today they occupy a central role in our contemplation of time manipulation, relativity, and the potential for journeys through the temporal dimension. To understand how black holes influence time, one must first appreciate their defining feature, the event horizon. This invisible boundary marks the point beyond which nothing, not even light, can escape. From a distance, objects falling toward a black hole appear to slow as they approach this horizon, their motion stretching ever more gradually in the perception of an outside observer. Time, in essence, dilates. The closer one gets to the event horizon, the slower time moves relative to an external frame. In this extreme curvature of space-time, the very concept of now becomes fluid, malleable, and deeply fascinating. This gravitational time dilation, a direct consequence of Einstein's theory of general relativity, provides a natural laboratory for exploring temporal manipulation. A traveler hovering near the edge of a massive black hole experiences seconds, while years pass for those far away. In this sense, black holes allow a form of forward time travel. Journeying close to the event horizon accelerates one's progression into the future relative to the wider universe. The effect is subtle, majestic, and entirely dictated by the fabric of space-time itself, not by any artificial mechanism. Rotating black holes, known as Kerr black holes, introduce even more intriguing possibilities. Unlike non-rotating black holes, Kerr black holes drag space-time around with them, an effect called frame dragging. In their vicinity, space itself swirls, twisting the flow of matter, light, and time. This spinning curvature could, in principle, create closed time-like curves, theoretical loops in which time circles back on itself. While these regions are likely inhospitable for matter as we know it, they tantalize physicists with the idea that the universe may contain natural structures capable of bending time in extraordinary ways. The mathematics of black holes suggests that under precise conditions, These objects might serve as cosmic time machines. By carefully navigating near the ergosphere, the outer region where space-time is dragged along with the black hole's rotation, one could, in principle, trace a path that looped through time. Though the energy requirements, tidal forces, and hazards are extreme, the theoretical possibility exists. Black holes are not just endpoints of collapse, but windows into the profound interplay of space and time. They reveal that temporal manipulation is embedded in the natural architecture of the cosmos. Observations of black holes continue to refine our understanding of these phenomena. The detection of gravitational waves from merging black holes has confirmed that space-time is dynamic and responsive, capable of oscillating and propagating distortions across vast distances. High-resolution imaging, including the Event Horizon Telescope's famous capture of a black hole's shadow, provides empirical evidence that extreme space-time curvature is real, measurable, and influential. These observations transform black holes from abstract mathematical curiosities into tangible objects whose properties illuminate the possibilities of time manipulation. The implications of black hole-induced time dilation are not merely theoretical. Consider interstellar travel. A spacecraft orbiting close to a massive black hole could theoretically experience years or decades, while the outside universe ages centuries. In this sense, black holes offer a natural form of relativistic time travel, accelerating travelers into the cosmic future. The effect is serene, almost poetic, illustrating the quiet elegance with which the universe stretches and warps moments in accordance with gravity's invisible hand. Yet these extraordinary properties are accompanied by profound caution. Approaching a black hole requires navigating extreme tidal forces, intense radiation, and the precise balance of orbital mechanics. Any misstep could result in spaghettification, the stretching and compression of matter under immense gravitational gradients. The cosmos allows temporal manipulation, but only in concert with respect, precision, and deep understanding. Nature, in this sense, is both generous and exacting, offering glimpses of possibility while imposing strict conditions. Black holes also provide a bridge between macroscopic relativity and quantum theory, a connection central to modern physics. At the event horizon, the interplay of gravitational curvature and quantum fluctuations becomes significant. Phenomena such as Hawking radiation, the slow evaporation of black holes via quantum processes, hint at the subtle ways in which time, energy, and information interact near these extreme objects. Understanding black holes, therefore, is not only about bending time, but also about comprehending the deep unity of the universe at its most fundamental levels. Philosophically, black holes inspire reflection on the nature of reality and perception. Time near a black hole behaves differently than far away, reminding us that our everyday experience is only one frame among many. The universe is layered, flexible, and responsive, and what seems absolute in our limited perspective may shift under conditions beyond ordinary imagination. Black holes are both teachers and mysteries. They reveal the rules of the cosmos while inviting quiet awe at its complexity. Finally, Contemplating black holes as agents of time manipulation encourages a serene appreciation of cosmic patience and scale. These objects, formed over millions or billions of years, demonstrate the slow, deliberate choreography of gravitational forces. They bend time not as a toy to be exploited, but as a natural process, subtly shaping the flow of moments across the universe. In this perspective, time travel is not a rush or a spectacle, but a meditation on the extraordinary ways the cosmos stretches, twists, and weaves the fabric of reality. Black holes, therefore, are more than astrophysical enigmas. They are natural laboratories for understanding time, showing us that temporal flow is flexible, dependent on gravity, and embedded in the structure of space-time itself. By studying them, we glimpse the profound possibilities of the universe, from relativistic acceleration to theoretical closed loops in time. They remind us, gently and profoundly, that time is not a rigid arrow, but a living dimension, responsive to mass, motion, and the invisible hand of gravity. Section 12. Cosmic strings and natural time loops. Beyond black holes, the universe may contain subtler, almost invisible threads that influence the flow of time. Cosmic strings. These hypothetical one-dimensional defects in space-time are relics of the early universe, formed during the cooling and symmetry breaking that occurred shortly after the Big Bang. Though never directly observed, cosmic strings are predicted by certain grand unified theories and have captured the imagination of physicists as potential natural laboratories for exploring extreme space-time geometry, including the creation of time loops. Cosmic strings are not strings in the everyday sense. They are unimaginably thin, thinner than a proton, yet immensely dense, with mass per unit length so high that even a kilometer-long segment could outweigh the sun. This density causes space-time around a cosmic string to be dramatically warped. Instead of curving space like a planet, a string creates a conical distortion, where paths that would normally be straight are subtly bent. Light, matter, and even the flow of time are affected, offering a gentle yet profound influence on the surrounding cosmos. The potential for cosmic strings to create closed time-like curves emerges from this warping. Imagine two cosmic strings moving past each other at nearly the speed of light, or a single loop of string twisted precisely in spacetime. In these configurations, the conical geometry could, in principle, allow a path that loops back to an earlier point in time. A particle, photon, or perhaps even a spacecraft navigating this region could experience a journey through time without violating the fundamental laws of physics. The universe, in its quiet elegance, may contain these hidden corridors waiting to be explored conceptually. One of the most fascinating aspects of cosmic strings is their subtlety and elegance. Unlike black holes, they are not destructive in the conventional sense. There is no event horizon, no crushing tidal forces, just a gentle warping of spacetime along their length. This makes them theoretically safer environments for probing temporal effects at least on paper. Yet their thinness and immense energy density mean that interacting with one would require extraordinary precision. Even a misalignment could nullify the delicate time loop or produce violent local effects. Observational searches for cosmic strings are ongoing, often focusing on gravitational lensing. A string's mass bends light in characteristic ways, producing double images of distant galaxies or subtle distortions in the cosmic microwave background. Detecting such signals would provide indirect evidence of strings and offer insights into how space-time can be warped naturally. Each observation, even null results, refines our understanding of the universe's capacity to stretch, twist, and fold time within its hidden structures. The study of cosmic strings also intersects with quantum mechanics. Quantum fluctuations around strings could produce exotic energy densities, potentially stabilizing space-time distortions in localized regions. In theory, these quantum effects might enhance the conditions necessary for natural time loops, blending relativity and quantum physics in a delicate dance. The universe demonstrates here, once again, that extreme phenomena often emerge at the intersection of fundamental forces where probability, geometry, and energy converge. From a philosophical perspective, cosmic strings evoke a profound sense of cosmic subtlety. Unlike the dramatic spectacle of a black hole, strings are quiet, almost invisible threads. Yet their influence stretches across space and time. They invite a contemplative appreciation of the universe's hidden architecture, suggesting that the cosmos contains more than what is immediately perceptible. Time, in this context, is not a simple line, but a textured landscape, shaped by threads and folds imperceptible to the senses, yet present everywhere. Moreover, cosmic strings highlight the interconnectedness of all scales. A defect smaller than an atom can warp space-time on galactic scales, reminding us that the microcosm and macrocosm are linked through geometry, energy, and gravity. Exploring these connections cultivates both humility and wonder, as we realize that the universe's grand design emerges from subtle, elegant structures rather than only from dramatic, visible phenomena. Even in the absence of direct evidence, contemplating cosmic strings serves as a meditation on possibility and patience. The universe may be full of hidden corridors where time can loop, fold, or bend gently, accessible only in principle, but still meaningful in concept. Studying these structures encourages reflection on the profound ways the cosmos operates beyond human perception, offering glimpses of hidden rules and extraordinary elegance that govern reality on the largest and smallest scales alike. Finally, cosmic strings remind us that time is flexible, relational, and layered. They demonstrate that loops, bends, and distortions are natural outcomes of space-time's geometry, arising from mass, energy, and motion, rather than human intervention. In imagining travel along or near these hidden threads, one is drawn into a quiet meditation on the universe itself. Vast, intricate, and delicately responsive, where even the smallest invisible structures may harbor pathways through time. The cosmos, through these subtle natural formations, whispers of possibility, balance, and interconnectedness, inviting both scientific inquiry and serene reflection. Section 13. Quantum entanglement and temporal connections. In the quiet, hidden realm of quantum mechanics lies a phenomenon that continues to astonish physicists and philosophers alike: quantum entanglement. When two particles become entangled, their properties become intrinsically linked, regardless of distance. A measurement on one instantaneously affects the other, as though the universe itself has woven a secret connection between them. While entanglement is often discussed in terms of spatial separation, it also offers tantalizing possibilities for temporal connections, suggesting subtle threads that might link events across time. Consider a pair of entangled particles where one is observed today and the other remains untouched for years. The act of measurement instantaneously collapses the combined quantum state, influencing the second particle's condition regardless of the temporal separation. This does not violate causality, nor does it allow macroscopic communication backward in time, but it hints at a universe where information and correlations are not strictly bound by conventional chronological order. In this sense, entanglement can be seen as a delicate, invisible thread connecting moments across time, a whisper of temporal non-locality in the fabric of reality. Physicists have explored how entanglement might interact with relativistic time dilation. When one particle of an entangled pair is subjected to strong gravitational fields or high velocities, for instance, near a black hole or moving at near light speed, time passes differently for it relative to its partner. Experiments suggest that the entanglement persists despite the temporal separation. This resilience implies that quantum correlations are woven more deeply into space-time than we might have imagined. The universe, in its quiet elegance, maintains coherence across time as well as space. Entanglement also provides a conceptual bridge to quantum teleportation, a phenomenon in which the state of a particle is transmitted to another distant particle without moving the particle itself. While this process does not transmit matter or classical information faster than light, it demonstrates that information can exist independently of local time and space constraints. In the grand scheme, this principle hints at a subtle malleability of temporal relationships at the quantum level. The flow of cause and effect remains preserved, yet the universe allows connections that stretch beyond our classical intuition. These phenomena inspire profound reflection. If quantum entanglement can link events separated in space and time, then time itself may be less rigid than it appears in daily life. Events are interdependent, correlations ripple across scales, and the universe contains hidden harmonies that silently maintain coherence. Time, at this level, is more a network of relational connections than a simple sequence of moments. The cosmos becomes a quiet, intricate web where probability, geometry, and causality intertwine. Philosophically, Entanglement reminds us that reality is not isolated, but interconnected, and the threads of the universe stretch far beyond the boundaries of perception. Each particle, each quantum fluctuation contributes to a subtle tapestry that links past, present, and future in ways that remain largely unseen. Though we cannot yet traverse these connections at will, contemplating them fosters calm awe. The universe is patient, precise, and infinitely richer than our immediate experience might suggest. In practical terms, entanglement provides lessons for understanding the limits of time travel and information transfer. While macroscopic backward travel may remain out of reach, the resilience of quantum correlations across time shows that the universe can maintain consistency and coherence even under extreme conditions. It is as if nature has a built-in safeguard, preserving the integrity of reality while still allowing subtle, elegant pathways for interaction across space and time. Ultimately, quantum entanglement transforms our perspective on time itself. It shows that time is not merely a linear arrow, but a flexible, relational dimension, subtly intertwined with space and energy. Through entangled states, the cosmos reveals that moments are never truly isolated. Each is linked to countless others, forming a harmonious, coherent web that spans both space and time. As we conclude this exploration of time, wormholes, black holes, cosmic strings, and the mysterious threads of quantum entanglement, a calm understanding emerges. The universe is a masterful tapestry of possibilities. Time, once thought absolute and unyielding, is revealed to be flexible, intertwined with space, matter, and energy. From the spiraling curvature near black holes to the hidden corridors of cosmic strings and the delicate connections of entangled particles, reality invites both awe and reflection. Time travel, paradoxes, and temporal manipulation may remain largely theoretical, yet contemplating them nurtures curiosity, humility, and wonder. The cosmos does not rush. It bends, folds, and resonates with a quiet elegance. In studying these phenomena, we glimpse the hidden architecture of existence, a universe both intricate and patient, where moments are not isolated points, but part of an interwoven, living network. In this vision, the journey itself, the meditation on time's mysteries, becomes the true marvel